Now let's examine the determinants of cardiac output during myocardial energy failure. I think we can already agree on one, rate. Right now the pump is in energy failure because of low, or in this case, 0 rate. If I increase the rate to 1 beat per minute, the maximal ventricular volume of 100 cc's is ejected and we have a flow of 100 cc's per minute. At 2 beats per minute, 200 cc's is ejected, and so on until the pump is going fast enough that the ventricles no longer have time to fill completely at this particular mean vascular pressure and inlet impedance. The pump is then back in energy excess. Clinically, we see pump energy failure in complete heart block at a rate of 20 to 30 beats a minute. If we increase the heart rate, there are concomitant increases in cardiac output until about 70 beats a minute, at which time the heart is no longer in power failure. Then further increases in pacemaker rate cause no further increase in cardiac output. So one determinant of cardiac output during myocardial energy failure is rate. The other myocardial energy failure state, which we are about to examine, is when the strength of contraction is insufficient to overcome an outlet impedance. Remember our earlier example where a strongly working pump was able to overcome an outlet impedance. But if the strength of contraction were insufficient, which is a condition I can simulate by manually contracting the ventricles, there will be a significant decrease in flow. The outflow impedance, together with the insufficient strength of contraction, limits the emptying of the ventricles. Therefore, they fill completely before the end of diastole, thus causing intermittent inflow. This limited inflow reduces pump output. Clinical corollaries are seen in all myocardial energy failure states, such as myocarditis, myocardial infarction, and aortic outflow obstruction with weak ventricular contractions. With the insight that we have gained from the model, you should be able to ascertain that Starling's law, which states that the greater the filling at diastole, the greater the strength of contraction at systole, expresses a mechanism of cardiac output control only during myocardial energy failure. At all other times, it has only energy conservation implications. You should also realize that Poiseuille's law, which expresses outlet resistance as a determinant of cardiac output, is once again only valid during myocardial energy failure. At all other times, it merely expresses the pressure gradient across an outlet resistance point. All available data from human physiologic experience correlates with the findings we have seen in the model. Therefore, I believe we are safe in presuming that the human heart is a non-sucking, intermittent outflow, continuous inflow pump. We can also presume from the model that cardiac output has two separate sets of determinants, only one of which can be operative at a time. It is the set that potentially limits the output most that is the determinant at any time. The first set is applicable when the heart is in myocardial energy excess and includes mean vascular pressure, which includes fluid volume and system compliance, and inlet impedance, which is the product of a resistance point and a distensible bed upstream from that resistance point. The second set of determinants is applicable when the heart is in myocardial energy failure and includes low rate and or insufficient myocardial contraction to overcome outlet impedance. You have now observed that most phenomena seen in the cardiovascular system need no other explanation than simple hydraulic mechanics.